Okay, thank you everybody for coming today. This is my master's thesis presentation on brain-aligned tactile representations for dexterous robot learning. And feel free to stop me at any time for questions. So robots today can already do some pretty amazing things, folding your laundry, factory assembly, cooking eggs, but most of these models rely very heavily on vision. This video here is from a humanoid robotics company figure. While it's cool, if you observe carefully, the motions are a bit unnatural. When I interact and open my drawer, I don't really need to stare at my hand the whole time to do it. I can open it with ease because I can feel. We can also do things like running your fingers over a roll of tape to find the edge, or digging through your pockets to find your keys. That's something that robots today can't do. They're numb. And robots are indeed well aware of this, so tactile sensing is quickly becoming a hot topic. It's the essential way forward to achieve safe and agile dexterous manipulation. But unlike vision, where we can use any camera, tactile hardware is incredibly diverse. The popular kind of sensor in research now is gel sight. It's just another camera behind an elastomer with little lights capturing the deformation on the surface. Visual tactile sensors like this one are high resolution, but can suffer from bulkiness and inconsistencies from sensor to sensor. Then we have magnetic-based sensors like U-Skin from Sila Robotics, Reskin and AnySkin, developed by Renak Baranji here at CMU. But these can suffer from hysteresis and temperature and material sensitivity. Meta then developed the multimodal digit 360 sensor, which measured pressure, audio, image, and IMU, so everything in one, also quite bulky. The X-Hand and Sharpa Wave offer integrated tactile sensors on their fingertips of their robot hand. Wuji offers a glove that has more coverage instead. And more of these are being developed with all sorts of techniques: optical, magnetic, capacitive, piezoresistive, triboelectric, and more. Then you have figures like Figure, who've said, forget all of that, we're just going to stick another camera in the palm and call it a day. So the landscape of hardware is so diverse because we honestly don't know what the right recipe is. And the big question I seek to answer is this: what kind of tactile representation do we actually need to achieve natural dexterity in robots? As a first step, I turn to nature. Evolution has already performed the optimization of physical sensors on agents, so why not borrow an existing working strategy? Many animals, like whiskers, have antennae to sense the world where their eyes cannot, like the cat. She grabs the toy with her claws, and as it approaches her mouth, she moves her whiskers forward to know when it's close enough to bite, all in a split second. Rodents can map out dark environments and distinguish objects using just their whiskers too. It's amazing, and one has to wonder, what's going on in those brains to process that information so quickly and precisely? Could we replicate this kind of ability in an artificial brain? With techniques from computational neuroscience, we can actually begin to answer this question. Traditionally, the Turing test is used to evaluate intelligence. It asks, is robot behavior indistinguishable from humans, or in our case, animals? For example, could you distinguish human speech from ChatGPT from behind closed doors? But this compares output behavior only. And just because ChatGPT can talk like a human doesn't mean it understands in the same way that humans do. We're interested in understanding what the brain is doing internally. And this is a Neuro AI Turing test developed by my advisor, Iran, and colleagues. Do our artificial neurons connect and fire in the same way that animal brains do? What kind of model architectures are the most brain-like? So this is our question, and to begin to answer this, we'll have to replicate some real mice in simulation, which we can then train artificial brains. We design our task around what the mice learn how to do: the ability to distinguish objects using only force feedback from their whiskers. We whisk a variety of objects in simulation using a biophysically accurate whisker array, modeled as a series of conical links connected by springs, arranged based on average measurements from real mice. For each of the 30 whiskers, 6-axis force and torque is measured at the base, so each object sweep consists of these forces per whisker through time. We sweep about 10,000 different objects with various augmentations per object, varying the speed, height, rotation, and distance. I will note that these objects from ShapeNet are not quite ethologically relevant to what a real mouse would encounter. But the point is that the models learn how to distinguish between all these different categories of things in general. As a sanity check, we perform a simple classification on 2, 3, and 4 classes from the dataset, just to confirm that each whisk actually contains information rich enough to be clearly distinguishable. And as you can see, that classification accuracy is all above random chance on both versions of our dataset. So now that we have our data, we can move on to selecting neural architectures that we want to train. Since no single temporal model is universally the best across all sequence modeling tasks, we have to systematically search over the space of temporal model architectures. Using an encoder-attender-decoder framework, we can easily construct new models by swapping out these modules like this. So starting from the bottom, we have our encoders. We can use various ConvRNNs, which has a local recurrent circuit. We can also use ResNet or state space models as well. The update rule for ConvRNNs look like this. So they have that local recurrence at each layer, hence that orange feedback arrows in the diagram. For the attender, we can include GPT, Mamba, or no attender. And for all the models, we use a simple MLP as the decoder. We can then train the models using either supervised or self-supervised losses, including SimClear, SimSIM, or autoencoding on our whisking dataset. With this, we have trained 64 different models total. And just to note, we have these temporal architectures and the EAD framework conveniently packaged as open source libraries. So, future research can take advantage of this. In addition to the sweep augmentations with the object variations we saw earlier, we also apply some data augmentations during the training process as a computationally inexpensive way to expand the dataset. Recall that each item of the dataset consists of the forces on the whisker array across time. We observed that applying traditional image augmentations, like blur, color jitter, and grayscale, made the models unable to learn at all. This means that these operations aren't label-preserving transformations when applied to tactile data the way they are in vision. Instead, we had to come up with our own set of tactile augmentations, including vertical, horizontal, and temporal flips. While not exact, these correspond to a much more natural transformation on tactile data, kind of like mirroring, reflecting, or time reversing the whisk. Using our tactile data augmentations during training increased both task performance, the top half of this plot, as well as the neural fit scores on the bottom half on our best performing models. Now, with our 64 models selected and trained on shape categorization, let's see how well they actually do on the categorization task. The bar plot here is grouped by the model's loss function, the self-supervised models, SimSIM, SimClear, and autoencoding, and then the supervised on the right. Focusing on the rightmost bars, these all happen to be variants of ConvRNNs, and they're outperforming architectures like ResNet on the tactile recognition task. We do note that the task itself is quite hard to learn through self-supervised alone due to how some of the classes in the dataset are quite similar to each other. So we found that the supervised models always perform better on the top 5 task categorization accuracy. With these trained models, we can then perform our neural evaluation against a real mouse somatosensory cortex dataset. We use representational similarity analysis, which is the correlation between the representational dissimilarity matrices of the neuron populations. Given to animals, we can compute the RSA over the true responses, where the average is over the source animals or subsampled source neurons, bootstrap trials, and trained test splits. This yields a vector of these average values, which we can then take the error over across animals. Since no two brains are exactly equivalent, we decide to use the maximal animal-to-animal score as our target ceiling. For model-to-animal consistency, we simply use the neural responses from our artificial model in place of one of the animals. We apply Braman-Brown correction to each term since they're correlations of observations from the half trials of the same underlying process, and then we can obtain our final noise-corrected correlation metric as follows. It's just a bunch of statistics. The real mouse neural data set that we are using, collected by Rogers in 2022, consists of high-density extracellular recordings for neurons across all layers of the barrel cortex as the mice move their whiskers to identify a shape as either concave or convex at 3 different distances. After filtering for valid trials, we had about 1,000 neural units across all the mice to compare against. So we recreate the same experimental setup and simulation and input those series of forces to our models to get our model neural activations. We can then perform the neural fit analysis to see whether our models processes this stimuli in the similar way that real mouse brains do. And here are our results. In our figure here, this leftmost animal-to-animal bar is the animal-to-animal neuroconsistency score. The mean is quite low, but there's at least one pair of animals that do highly correlate with each other. So again, we focus on that max score. And in the bar plot, the lighter bar on the left actually represents the untrained versions of the models. A question I usually get is, how are the untrained models able to correlate so well with the mouse brains? Well, randomly initialized networks are functions. They're already pre-selected to perform the task well when trained. And this is a well-noted phenomenon in neural AI across regions, that architecture really does matter a lot. By doing this comparison, it allows us to isolate the contributions of the architecture versus loss functions for each pair of architecture and loss. The models on the right that saturate our noise ceiling are noticeably improved when trained. The highest neural fit score are intersection RNNs, which are ConvRNNs with a coupled depth gate in addition to a recurrent gate. When we look at the fit scores per layer, we can also see that the later layers tend to have a higher neural fit, which suggests that hierarchical processing is helpful to match the brain. So the primary takeaway from this is that ConvRNNs, and actually a self-supervised ConvRNN, best predicts real mouse data on whisking. So that answers our original question. In summary, we've almost saturated the neural fit ceiling, meaning we've pretty much passed that neural AI Turing test. Our simulated mouse brains do the same thing that real mouse brains are doing. And we've shown that ConvRNNs generally outperform the feed-forward and state-space models on shape recognition using those realistic tactile forces. Also, our results indicate that contrastive self-supervised objectives can match the supervised neural alignment, meaning that it nicely suggests that there's this more general purpose representation in the somatosensory cortex. So we now have a better neuroscientific understanding of the somatosensory cortex, and the implication looking forward is that self-supervised ConvRNNs could be a promising model architecture to further investigate in force-based tactile sensing applications. I'm proud to share that this work was accepted as an oral at NeurIPS last year. I can pause here for questions. Okay, so we found that simulated forces and torques can match real brains. The question is now, will our strategy of taking inspiration from biology still hold when applied to robot tasks? I want to return to this picture here and emphasize there's a lot of ways to proxy tactile data implicitly as an RGB image through the little dots you see, the elastomer marker motion. You could use pressure readings, you can use contact microphones, and it's unclear for robotics what's sufficient. It's also really hard to make a fair comparison. Realistically, no lab could afford to buy and test each of these sensors in the same environment. So I turned to simulation. Just 2 years ago, even just 2 years ago, tactile sim was considered too unrealistic to be useful at all. But that's changed now. Policies trained with simulated tactile sensors can directly transfer to the real world on both visual tactile and magnetic sensors. And just to illustrate my point on the advantage of simulation, this is a real robot hand that we have in the lab. It costs $16,000 and it comes with tactile sensors on just the fingertips, each resolution of like 12 by 10. But using simulation, we can extend much beyond this and vary the tactile type, the fidelity, placement, and resolution for any robot embodiment at massive scale. But no existing robot simulation engine had these capabilities, so I had to build one. Here's how it works. In a rigid body, soft contact physics simulator, so the underlying physics could be Isaac physics. It could be, Mujoko. Here I built it in Genesis World. Uh, for the object in contact for every probe, we measure the contact depth using a signed distance function or raycasting. We call this raw reading the contact depth probe. Building on that, we obtain force torque information by tracking the object velocities. We can also mimic the deformation of an elastomer-like gel site by tracking points on the target object. We can even mimic proximity sensors by tracking points within sensing range. For all sensors, we can also simulate imperfections like hysteresis, crosstalk, and drift, which are notable limitations of currently available tactile hardware. These tactile probes can be placed anywhere on the robot at any density. It's completely agnostic to the robot embodiment. And thanks to per-probe parallelization and point query accelerations, we achieve massive scalability, enabling fast reinforcement learning. Previous works have a similar claim about RL, but not at our scale. We can easily scale past 16K environments, whereas previous methods typically end up crashing from inefficient memory usage. So even in this tactile policy rollout here, the previous paper used just one tactile sensor on the robot gripper. We have 5 sensing areas on each of the fingertips, and we can see that we can scale way past, it can go up to 1632K, but they only report up to 1000 in their paper. TacXL is a tactile simulation method currently integrated into Isaac Lab. It was quietly released around January this year. And based on their reported numbers in their paper, we have 3 times faster throughput. I know it doesn't look like it, but this is a log scale here. So that's 3 times faster throughput and just visually much more stabler tactile force readings. So using the simulated tactile sensors, we can train tactile policies and compare their task performance, yielding a quantitative answer to our big question. We first train a privileged teacher policy which has access to the object state. We then distill many tactile students, replacing privileged state with tactile signals. We evaluate on 3 different tasks and vary the sensorized area. So just for the in-palm rotate task, we compare fingertips only versus having across the whole like mid-finger and palm area. And then we train 9 different tactile representations per task. The ag prefix indicates that for each sensing area, for example, the tip or the palm, we kind of average those forces together, whereas the rest of them are per taxel. So each dot you see would be an actual input to the model. We can clearly see that proprioception only is not enough. They are trailing the bottom there because, they can't feel a thing, they can't see a thing, there's no vision involved. So they're unable to learn, which is not terribly surprising. But we do find that whole hand sensor placement matters a whole lot more than sensor type. Now, this is interesting because like the real robot hands that are currently available, most of them have fingertips only. But depending on your task, having just even a few sensors on the palms can really make a big difference. Across the tasks, we see that policies with 6-axis force torque tactile data, which is that red line, as well as the green line, consistently outperform those with force-only, binary, or elastomer marker motion. Next, fixing kinematic force torque as our representation, we vary the tactile resolution and added some imperfections, like that crosstalk and drift I mentioned earlier. But we actually find that those don't affect the performance nearly as much as the placement and type do. So together, these findings provide actionable suggestions for improving the next generation of tactile integrated robot hardware. I'm also proud to implement the first temperature sensor in a robot simulation platform, because some hardware like the Digit 360 and the X-Hand actually do come with temperature sensors, but they're hardly usable because they lack the sensitivity to be useful. They're behind rubber, and the hand itself also heats up too. So it's more like a health check reading than like to actually be used for temperature sensing. We perform a lightweight experiment ablating these thermal properties on the robot hand to understand how sensitive does it actually have to be able to be useful. In our case, to learn to distinguish a hot object from an otherwise identical bin of objects. In our task setting, since the contexts are really brief, since this is trained on RL, we find that a really high conductivity is required for the temperature sensor to be useful. Right. As a proof of concept, you're gonna have to, I wonder if this can be heard from the Zoom, but as a proof of concept, I implemented a contact audio in simulation as well. Because rigid body physics alone can't capture detailed material properties. But by layering modalities like temperature and sound, we could have scalable simulation of really information-rich environments. So in this case here, the time step of the actual physics simulation would be stepping at, say, like 0.1 seconds, 0.01 seconds. Um, but here the audio frequency vibrations operate at thousands kilohertz. So just based on specifying some material properties, you can synthesize, and this is actually pretty well-known techniques in game engines and for experimental rendering and such, that we can borrow and use in robotics to make things a lot more realistic and to be able to scale environments and variation better. It's possible to use these tactile and temperature sensors right now with Genesis World, which is the latest physics and rendering engine for robotics. During my internship at Genesis AI, I actually built the sensor pipelines. So like the temperature sensor, IMU, LiDAR, the tactile sensors, of course. I can't take credit for the video, they did the rendering, but that's there, and all the code is open source. And so that paper is currently just a preprint on arXiv. Any questions about that? Okay, well, that concludes my contributions for my master's thesis. Um, just to summarize and synthesize between these two works, I think the biggest takeaways are as follows. Six-axis force torque is a biologically faithful, and independently, we observe that it's a robust tactile representation for learning dexterous tasks. Sensor coverage is going to beat high resolution. In animals, super high sensitivity and resolution is reserved for only very small areas. And we saw in the ablation experiment on the robot hand that increasing resolution really doesn't increase task performance as much. Finally, consider ConvRNNs, or at least something with local feedback and recurrence, as your architectural choice for tactile processing. In our robot experiment, again, we used a combination of MLPs and RNNs for the tactile processing. Okay, and these are all the familiar faces I've come to know over the years, and I'm just very thankful for everyone for supporting me. Okay. And I think that means it's like time for we'll take questions. Yeah, it's questions from the audience first, and then questions from our committee. I'm sorry, I have to stop the share to see the chat.
Listening. Joshua.
Okay. Yes, hello, you can go on ahead.
Thank you so much. That's a super interesting talk on both the papers. I'm really interested in the whiskers and the sort of mouse analogy and thinking about. I love the whole approach of really thinking about trying to model how physical intelligence is developed in rodents, and I think that a lot of that's missing from the large language model focus that everybody's so focused on. So I think this is great. I guess I'm thinking about my question is really about the representation part.
Mhm.
And I mean, rodents have really sophisticated representation learning, and they don't sort of have these sort of prefix object slots. I mean, I know that the whiskers do correlate with specific neurons, but the way that then representations are built bring in all sorts of context and And they're forming object representations in part through learning in ways that aren't sort of fitting into pre-configured slots. And so I
Mhm.
guess I'm wondering whether and how, and if so, how you're getting at that kind of object learning through experience and doing that kind of representation. Because yeah, so can you
Yeah.
talk a little bit to those kind of representation questions?
Yeah, of course. So, the best really neural data set that we could compare with was, very limited. It's through the somatosensory cortex, but re I mean, really just that barrel cortex. But like you said, that omits sort of like any sort of memory or associations that these animals might have and pulling from other parts of the brains, which I definitely think we should collect more neural data for to be able to do these evaluations. But primarily, like our choice of task and our choice of representations was limited and specifically scoped so that we can do a more fair comparison against the neural data set that we had. But I think it would be great for, neural tactile community if there were better available recordings, and as well as like active whisking is also really important. They're not only just feeling as things move towards them. It's like they're the ones, going in there and deciding which ones do I need to touch more to figure what this thing is. So I definitely think that the current paper is missing that. But as a purely computational side, that's not something I can address. But I do hope, I did present at Neuros, and that was definitely one thing that I pushed for. Yeah. Does that answer your question? I'm not sure I took the right angle there.
Yeah, I mean it's a start. I mean, it sounds like you're thinking about those things too a little bit, and um, yeah, I just wanted to know how you're thinking about them. But I get it that that's not really covered in the data set that you're working with. Um, I mean, I guess it is sort of a proximate question and a little
Yeah.
separate from the question that you were answering. It would be, from my view, it would be I'd like to see sort of an exploratory world modeling where, where there's I think that that's the direction that robotics is going to have to go.
Yeah.
I don't think that the cramming it all into one big brain is actually going to work. I think
Yeah,
we're
yeah.
going to need sort of a much more
Yeah.
exploratory.
Oh, and definitely like fusion. This would be like future work, fusion with tactile and the proprioception, so like kind of like the active whisking part. Um, because right now typically we only use like concatenation, with the features, but if there's actually feedback, so because those are very well connected actions, even though they're different modalities, would be definitely useful for future research that we've been thinking about. And I hope that we do move towards in robotics as, people are trying to integrate more sensors than just cameras.
I mean, I think
Yeah.
the real goal is to try to have it be in an agent.
Yeah. Yep.
Oh, here, I can unmute.
Okay.
I think it's a good, I, I think the real goal is really to have it in an agent. And that was the kind of motivation for us. Um, it's just that, it just seems so obvious that agents interact with the world in this way. And so we just wanted to get the rudiments of it going, to ultimately put it in a kind of multimodal system. It's just sort of quickly became clear, once we did the mouse work, it was nice to validate that the ConvRNN was a decent architecture as a brain-like system. But then we were really curious, does it still hold in like real like hard tasks with robot hands? And so that's kind of what motivated this other thing. And it was cool to see it also kind of emerge as a useful architectural prior there. And now I think, I mean, from a neuroscience point of view, I think the neuroscientists would love to see a rodent agent that has all of these things in it. Maybe for us, it's a bit more um, interesting to really have the agent be a humanoid and have it do the tasks that we care about, but still the same principles of multimodal sensory integration with tactile sensing all in the loop as part of that. So it's kind of just first figuring out you're trying to build a house, like just having the foundation or the basement first, and then yeah. So yeah.
Absolutely. I mean, I think that's so from my perspective, part of why the rodent is really interesting is just because it's lower on the foundation, right? So it cuts out some of the noise of all of the sophisticated stuff going on with humans. But I mean, that would be amazing to have it be, a anthropomorphic sort of robot where you have the sensors on the hands or whatever. But I mean, that's exactly the direction that I've been thinking about is in terms of, what happens when you put an agent in the world. And it seems to me that most of the Latin world model RL really falls down in that if you look at like Dreamer v3 or TD MPD 2, it's like you're compressing the whole situation into one Latin representation, and you're not able to really get at object representations at all. And so it seems like if you could sort of attach this kind of very nuanced sensory, touch to exploration, that really would force you to have some way of dealing with that problem.
Oh, absolutely.
Yeah, thank you. Do you have any other questions? It's fine, yeah.
Speculations from the audience.
Okay, I guess that's fine. Um,
So should we do, do we do the committee?
it's for like PhD. I honestly no, like I think it's so chill for MSR. She didn't even say I had to do anything, you know. Hi, Akash.
Hello, I do have questions.
Okay.
Yeah, great. Excellent presentation and talk.
Thank
Um, yeah, I had a bunch of questions about the first paper as well as the second one.
you.
Um, I guess like for the first one, like how much does the surface geometry of the mouse nose itself matter, and how much does the distribution of the whiskers matter? Like when you simulated them, did you simply randomize the locations?
Oh
Um,
no, for the mouse, I mean
mhm.
they have 30 whiskers. I mean, I guess they can lose whiskers and things, but that's um we didn't do like a masking kind of thing either, but it's fixed just for the mice. We just use like the average mice measurements since they don't provide like we don't have the individual exact locations of the whiskers per mouse, so we're just kind of
I
using the
see.
um so you know there's not too much variation there in
Interesting.
in
Okay.
testing on the mice, yeah.
Yeah, and okay, that makes sense. Like my second question here is like maybe before that, let me preface it. Like for your second paper, did you use the same ConvRNN architecture, or did you use something else?
Yeah,
Basically, the high-level
I actually
question here is like broadly, like if you had more data, say for robotics tasks, like would the the architectural recommendation change, or would you still say that this holds? That ConvRNNs are pretty good.
I think that's an open question because like for the first paper, we were focusing on architectures, but not just to do the task well, but really comparing against real brains. And then in this one, I kind of just jumped in and used the ConvRNNs, but I haven't done like a super detailed like search of the architectures, like but now that we have the simulation, and there's actually a lot of other papers releasing larger tactile data sets, now that we have these available, I think you know a large search over architectures for tactile optimizing tasks is is pretty valuable to do. But I would say I'm not sure yet, just based on the data we have. Like a lot of people in the past have done clever things with tactile architectures, like GNNs, since like you can kind of like connect this graph. Or like you can the idea for the conv is you just like pad out the space, have it be a grid, but like pad out the space. But then of course on a hand, like the fingers are moving in relation. So you could do all sorts of fancy like, graph, your choice of like what's considered adjacent. Um, and also how you're going to fuse it with everything else, like proprioception. And this was really going to be like research down the line. If I were to do a PhD, is what I would have done. Yeah.
I see.
Yeah.
Okay, okay. Um, About the tactile genesis work itself, like
Mhm.
one question that I probably did not fully get is like how do you compute the contact depth itself, or and like how much does that depend on the underlying
Mhm.
like rigid contact physics?
Mhm.
Specifically, like the main point here is like, if you're doing something like physics, right? You have
Yeah.
like single point contact between convex bodies, and
Mhm.
that keeps shifting around. And
Mhm.
how much does that affect your contact depth reading
Yeah.
itself?
Yeah, so that's the
Yeah,
thing, is that the physics is separate and the sensors are lying on top. So the physics step does this thing. And I know that, this physics solvers will output like it'll do like box or whatever. It'll find like the points of contacts that it needs to calculate the correct like physical force, separate objects and things. But for us, with the tactile sensors, what we want is much different. We're trying to just query from arbitrary points, like anywhere on the hand, not necessarily, the physical like support point, which is ideal for calculating like the physical force, but to query on arbitrary points. So it's again ray casting literally just like, ray casting just like from in to
nice.
inside because now, I'm not incredibly familiar with physics, but Mijoko and Genesis you kind of uses Mijoko's like soft contact model. So rigid body meaning that none of the objects can deform, but soft contact meaning they're allowed to penetrate a little, which is what happens is like you hold something and uh, in the physics engine it's represented as the meshes colliding. So that's what we're measuring, and as you saw in the paper and previous papers, which previous like being like this year papers, show that yeah that is actually going to be enough.
I see, I see. And like I know this is very new, but like there are
Mhm.
like newer physics engines, like like Newton physics
Yeah,
engine, which do support hydroelastic contact,
yes.
right? And they're like you're pre-computing an SDF and essentially doing raycasting, but like in a pre-computed manner,
Yeah. Yeah, I'm
right?
so I use raycasting or STF. The SDFs and Genesis are also pre-computed. Um
Hmm.
and yeah, I think Genesis physics and the Newton are kind of in like a little race, and as well as
I see.
Mijoko. Like they're all kind of in like a little race, to see who can get the better and more stabler performance. I think they all have, slight nuances, what's better and what's worse. There's no single engine right now that's like better than the rest across all tasks. So yeah, it's if you're like looking to decide which is going to be better, it's actually quite hard to say now.
So yeah, so when you do like raycasting here,
Mhm.
like do you like literally sample on the surface of the two bodies and then you're raycasting from each of them to find distances?
Yeah, so kind of like the picture, it was like, there's all like the little probes, and like from each probe, we have the surface normal. So we just like raycast in the direction of the surface normal. Or if you're using SDF, then you just use a pre-computed SDFs to compute that.
I see. And how do you convert the distances to forces, I guess?
Now that is up to the user. So, every kind of like, nothing in real life is perfectly rigid. But you can just literally as like a linear spring, it's
Okay.
like
It's just a linear model. Okay.
yeah, you can
I
do a
see.
linear model. There's you can add an exponent onto it, but all those like, physical little parameters you can tune on the sensor to match your real sensor to your needs. I feel like there's enough like, tunable parameters that you could pretty much match most sensors, real life sensors pretty well. Of course, it's not going to be able to like detect magnetic field and things like that yet. Um,
Mm,
but if you add enough like the imperfections, like just like drift, the hysteresis, meaning like, when like coming into contact or getting out of contact like creates like drift and things like that. So I think it's like a fair spread of tunable parameters that could be used to approximate real hardware now. But of course, if you want to really be able to like, sim clone, like exactly sim to real, it may require even, collaborating with the hardware manufacturer themselves to really understand like the details and do sysid, which yeah, I haven't done that, but we do show it's like, and previous works have shown it's like, you
I mean,
know,
you have to leave some for the rest of us, right? No, I'm kidding.
yeah.
Uh, but no, this is pretty cool work.
Yeah.
I definitely think like, like spending more time with like tactile simulation is
Yeah.
helpful, even though like,
Because when I
yeah,
first talked, you said like you and Kenny too. When I first talked to Kenny Shaw, he was like, "Yeah, I gave up on simulation because this doesn't work." But now it does. It's times have changed.
yeah, right. And just maybe one final question I had was like, I didn't look at this carefully in your presentation, but did you like ablate the utility of normal and shear forces versus just like contact locations and the distribution of the contact on the hand for these tasks?
Normal and shear. So let me look at the okay, let me try to pull up the slide for the so I think it's easier if I show. But it's like we have like the forces is XYZ, so that's like includes shear. Force torque is shear and twist. And we have depth only. So if I just pass the raw depth readings, I'm just gonna do this. Um, yeah,
I see.
so just looking at this part, if you we have Booleans and then force has shear. Proximity. Now, in the simulator, I expose like actual having force and torque in the proximity, but you could also like, just take the magnitude and like ignore those shear values as well. Um, and note that I find the elastomer line actually really interesting because it's the elastomer marker motion, which is like the dots on the gel site. And if you think about it, like each dot now, because there's all that like local displacement effect, each individual dot is a lot less informative because like, it could have moved to the right because of shear or because there's something else next to it, that's being indented. So you actually lose information when you have small contacts, but like all this deformation,
I
local
see.
effects caused by the elastomer. So I think there's some things to be taken away from this.
Got you.
Yeah,
Cool.
and
Yeah.
Boolean's always bad. Uh, it actually performs fine on the screwdriver task because the teacher policy in this case is like almost vibrating, as in like it's like tapping very quickly to keep it spinning. Not super naturalistic, but in a scenario where it's like, your like contact is so brief, like binary can be enough. But
Yeah.
in the in palm rotation scenarios where it's like constantly in contact and like being pushed along the palm, it's really important to have like information on how, where in the palm is it? Did it slide one in like 0.1 centimeters, or did I accidentally slide it like a whole 2 centimeters? So that information becomes really valuable.
Makes sense. Yeah, I guess like in my experience as well, like in-hand
Yeah.
rotation task itself,
Yeah.
like it's not a great task to show like tactile
Mhm.
utility,
Yeah.
because like mostly you can do a lot with just proprioception there.
Uh-huh.
Um,
Yeah.
but
That's the
yeah,
other
yeah,
thing is that when people say like dexterous manipulation and in-hand reposition, it's like just doing same rotation or like any going to any orientation, or like if the objects are all circular versus if it's like really like long on one side. It's like those things completely change what the right kind of behavior is. So yeah, I think that's and the best tactile configuration is always going to depend on the specific task. But if you want the wide coverage and be able to generalize this, you know, coverage on the hand is seems to be the answer.
yeah. All right. Thank you. That's me.
All right. Thank you. Okay.
Yeah, so I have one question maybe.
Yes.
So yeah, fantastic talk, fantastic slides.
Mm-hmm.
I want to ask the following. So when we try to answer the question, how should we put tactile, right?
Mm-hmm.
Like what type of tactile and where we should place it, etc. I'm
Mm-hmm.
wondering if it's enough to just say, okay, I'm gonna make a simulator. I'll vary them, I'm gonna decide how to simulate this tactile
Mm-hmm.
signal, and then I'll do reinforcement learning for different tasks and decide versus do it all the way from sim to real, because different placements and different readings may have different transferability to the real world. So because at the end you care about the deployment of the sensor in the real world,
Mm-hmm.
it might have been I'm wondering if you think there is value on, varying the configuration, training the policy.
And testing the transferability in the real world.
Right. Now, for this, unfortunately, you also need hardware. So you need to evaluate specific hardware solutions out there right? But I'm just, because this doesn't exist, I'm wondering, do you think that things can collapse because of this transferability, black box right now?
I think the properties that physical simulation struggles with is like detailed friction interactions. So if like you've got like kind of like a fuzzy like woolly surface, like I don't know, like Velcro, it's like you might like unexpectedly get caught on something and things like that. But I think I don't see a clear reason why like there should be like some that absolutely detrimental factor in translating to real. And I think one part of this is that real tactile sensors of tactile hardware are getting a lot better. I mean, I recently looked at some new hardware stuff and like they can get very accurate like force and shear readouts and things like that. And I think it's like, both the hardware is improving to reach almost like the levels of like a perfect simulation kind of thing. So I think since these are both developing in tandem, yeah, I don't see a reason now why there would be like, and I think a simulation can faithfully transfer it, just given all these new techniques that we have. Sorry, that was a bit of a ramble, but of course I'm biased. Of course I'm biased, but I think it of course really depends on the nature of the task. If you're dealing with mostly rigid objects like say boxes in a factory and metal screws and things, you're not going to have much of a problems. If you're in a house that's dealing with a rugs and cloths that have like strings all over the place, you know, you might deal with some issues there, but that's not really due to it.
To the tactile. I mean, the carpet in the first place is hard to simulate, right?
So
in that sense.
Yeah. So I think forces are forces. I mean, physics has been understood, for centuries now. So I think fundamentally that doesn't change between our simulated and our real.
And how do you think tactile should be incorporated into robot policies? I think it's interesting how, like it's not exactly like vision, right? Because vision, even if I'm far away from the object, I can tell you where to go, maybe. But once you go and make contact, then, they can take over. Moreover, I would imagine that they're much more high frequency, let's say, than so what do you think about that? Yeah.
Yeah, it's interesting because biologically we have like the very low level control loop and then the higher level planning loop. And I think that real robots should also start to look like that. As you said, it's like, we look at one thing and I can look somewhere else and I can still pick up my phone. So that's the kind of thing that we want to enable with our choice of architecture. And also even that like if I notice something slipping, I don't need my brain to say, oh no, it's slipping. I just like my finger just reacts immediately. So that it really becomes you would get like quite a spaghetti of an architecture with all the different loops going on. But I think, something that has a lot of that feedback, across vision, across, the tactile, and to build up. Like we have a lot more data now. Like a lot of people are working on collecting good tactile data, and I think also getting like good like kind of a cautious work on like the like self-supervised like representations we can then take advantage of. But architecturally, that's not my expertise. So
Well,
I think
great.
we'll need a combination of many things now.
Well, in any case, fantastic work. I think it's very useful. I mean, improving simulators is always very few people work on it and very, very important.
Thank you. Hi, Joshua.
I just had to chime in. I mean, I could be totally wrong, but I wanted to pick up on the question of sim to real.
Yeah.
Because I guess my suspicion would be that even without dealing with the contact dynamics and all the complexities that you get into in real dynamics, that even just the question of irregularity of the objects, both in terms of recognition, so sort of the first paper was more about recognition, and then also then in terms of manipulation, that those irregularities in real objects are very consequential. And so I guess I'm skeptical that it just applies directly without doing some pretty extensive work around how you deal with those irregularities in both object recognition and also what happens when you go to manipulate it in a particular way.
So the current strategies, and even if you look at like pure like VLAs, like what they do is they do all the domain randomization in simulation, right? So even like somewhat unrealistic like disco colored rooms, and like they'll throw all sorts of crazy like randomizations at the policy, so that it can learn to become robust to those. So it's also on the policy behavior level that if you like learn a way to do the task such that you don't get yourself into those situations where you're like scraping against the like weird edge all the time. So on that policy level, like we we have one strategy against that, which is to add a lot more randomizations, which I also enable in the simulation by having all those imperfection parameters. At least that's the way I think about dealing with them. If we give in simulation an even harder problem that they would encounter than in the real world, then we can kind of hope that like it would be robust to any strange perturbations in the real world as well.
I mean, I guess it would be great if it, when you go to real, then it would be great if it works that way. I guess I'm a little skeptical, but I hear the random the randomization could help. But yeah, thank you.
Yeah, no, it's a fair point of view. I'm optimistic, but I know the more experienced people who've done more sim to real or know that you do encounter a lot more problems. I've been happy in simulation there. All right, I think okay. Thank you so much again, everyone, for the wonderful questions and for your interest in my work. And I guess I'll end the meeting now.
Thank you. Congrats.
Thank you.